because in fact, when we have a program over a finite field, the size of the finite field can be abstract, and you can actually run this program over many different extensions of a finite field. So more simply, you can run the program for many different finite fields. And then the universal equivalence asks if two programs are equivalent, even if they run on all possible finite fields. And then decidability is not trivial anymore because you have to check for all finite fields that the two programs are equivalent. And leveraging some algebraic tools, we were able to solve this question. Yes,
okay,
that's it.
Okay. Okay, thank you very much. So if you have any question, please just open your mic and ask them. And if not, I have a question.
Okay.
So in your definition of the equivalence for two probabilistic programs, you asked for the equality of probabilities. So I was wondering if it was reasonable to just to test this equality of two real numbers, or if you could relax this this equality to measure the distance between the two probability distributions or such ideas.
So it's actually, the answer is yes. It's some kind of approximate equivalence. And we actually wanted to look at it because we come from the world of security. Yeah. And it's quite often that we look at what is called indistinguishability. And it's some kind of approximate equivalence. So we looked at it, and we are starting to have some results, but it's instantly way more complex, let's say, because you have to kind of, you want to be able to bound the distance between two programs. So you have to do some complex operations over the distributions. We are able to bound the distance if you, well, in fact, the big question is what kind of distance you want to consider over the probability distributions. And multiple distance don't have the same interesting properties. So we can do it for some distances that are maybe not the ones that are the more interesting. And we cannot do it for the moment for the classical statistical distance. And we are trying to do it.
Okay. So is there a question? Another question?
There are no questions on Slack, and I don't see questions on the chat either.
Okay, so I have another question. I have plenty of questions, I'm sorry. So in your talk, you say that you start by saying that you do not consider loops because because there is something complicated that I didn't catch. So can you say some words about that?
Yes, well, in fact, if we add loops to the programming language, universal equivalence becomes undecidable. It's not proved in this paper, but we did it afterward. And in fact, you can encode two counters Minsky machines using the fact that we are looking at finite fields that are bigger and bigger and possibly of infinite size. You can use the fact that with some probability and in some big enough finite field, you can perfectly simulate a Minsky machine because you can use the size of the finite field as a bound on the size of the counters that you can have. And then if you are able to encode a Minsky machine, you can do a bit of encoding and then use the halting problem and its undecidability to show that universal equivalence is undecidable.
Okay, but it's still interesting to have loops. So can you imagine some approximated method or something, some way to how to say it, to not face this undecidability?
Well, to be honest, I think that there are some behaviors of the universal equivalence that we don't completely understand yet. Because well, this idea that you can, we are running essentially we are running the program with some parameter, and the parameter kind of specify how much memory your program can use. And so we are looking at programs that at some point will run with as many memory as you want. And then if as soon as you give the programs some constructs which allows them to exploit this infinite memory, I think you are in trouble. So I'm not really sure what could be a restriction on the kind of loop you can do that will not raise this issue, essentially.
Okay, so you mean that you will never be able to tackle loops?
I don't know which kind of loops we could tackle.
Okay, I see.
Well.
I have a question.
Yep.
So Charlie, in table 2, you have these various complexity and decidability results. So most of them have you have completeness results, meaning you have a reduction both ways. You have this reduction to positivity in the case of Q infinity zero majority programs without inputs. Now, I was just wondering, do you have a reduction the other way as well?
No,
No,
not
okay.
yet.
I see. So conceivably, you could, so you reduce to positivity, but positivity seems very hard. But conceivably, it's conceivable that you could solve this problem without necessarily resolving positivity.
Yes, the thing is that from all programs, we can create, we can instantiate some LRS, which is interesting with respect to positivity. But we believe that we can only create a subclass of all the possible LRS. And it's really unclear if from any arbitrary LRS, we can create the converse program.
Yes.
And I will guess that no, because we have, it's a very specific kind of LRS that we build.
Yeah, so the kind of LRS that you have, if I recall correctly from some of our discussion, although it's a bit hazy now, the eigenvalues, the characteristic roots are very particular, right? They're simple for one thing, and they're not.
Yes, we only have simple LRS, yes. So
and
that's,
they have, so that's one restriction. Although positivity is still hard for these things,
yes.
but there are some further restrictions. Is that correct? On the eigenvalues, on the shape of the spectrum.
So yes, but I would have to remember what is the actual restriction. No, I don't remember it at as
okay,
is.
but it's interesting. Maybe it is still hard for some subclass of LRS. I mean, this was just a thought, right? So.
Yeah, and if you have afterwards answer to that question, please come to the Slack and talk with Joël on Slack. Are there any other questions? Okay, so thank you very much, Charlie. And we move to the next paper, which is by Alexandre Goy and Daniela Petricsan on combining probabilistic and non-deterministic choice. So Alexandre and Daniela are there. So, okay. Perhaps Alexandre?
Yes.
Speak? Okay, can you give us just a summary of your paper?
Yes, thank you. So we try to combine two monads on sets, one modeling the probabilistic choice and one modeling non-deterministic choice. But there is a problem doing this because it is known that there is no distributive law of the required type, and there is even no monad structure on the composite functor. So what we did is that we remarked that there is actually a weak distributive law of the required type, which formula is here. And it is weak because it does not satisfy one of the required diagrams for distributive laws. The diagram presented in this slide. But never mind, what we did is see after that this weak distributive law corresponds also to a weak lifting, which is actually the convex power set monad on D algebras, which was a lifting known in the literature, but not explained in a systematic way. So people didn't know very well the origin of this monad. And we also get a monad on set, which is also a known monad, the monad of convex subsets of distributions. Finally, this framework is useful because weakening the notion of distributive laws does not inhibit classical constructions such as generalized determinization. So we can do the generalized determinization of probabilistic automata. We also get presentation for composite algebras, and we also get, though it's not in the LICS paper, we also get soundness of up-to techniques. And so many of these results were known in the literature, but not explained. And our framework brings the origin of all this nice framework. Yeah. Thank you.
Okay, thank you. So there is a question by Jeremy Cubans, who is here, I think. Perhaps you can ask your question directly.
I could.
Yep.
Alexandra has actually already answered it in the Slack.
Yeah, but if you can just make a brief summary of your question.
So I thought the construction was very nice, and convex sets of distributions is in a sense clearly the right model. It's the one that people have constructed from first principles. And I'm just wondering what breaks when you lose one of the axioms of the distributive law, a strong distributive law, in weakening it. And I worried that some sort of natural programming law would cease to hold, something like associativity of composition or units of composition or bracketing of groups of blocks of code or something like that. And I mean, Alexandra's answer was no, it all still works. It all still works because it all still works for convex sets of distributions as we knew. So I'm still a bit puzzled as to why those seem to be needed for normal distributive laws and why weak distributive laws are sufficient. But I'm satisfied with Alexandra's answer.
Okay. So
you don't want to say anything more?
See, maybe. So the key point is that there is no monad structure on the composite PD functor. So what breaks when we do our construction using weak distributive laws is that we cannot see anymore the composite functor as well. We get a monad structure on a new functor PCD, and what breaks is that this functor PCD is not PD.
Sure.
In a sense.
Yes, and but anyway, consideration of a few examples tells you that PD is not what you want.
Yes.
People have already discovered that the hard way, and you've shown a less ad hoc way of coming to the same conclusion, which is nice.
Yeah, thank you.
Okay, are there other questions? Okay, so there is also a question from Unread Trainee that you already answered, Alexandre. Perhaps you can just say something so that everybody can hear what was the question and what you wanted to answer to her.
Yes, okay. So the question was about applications. How can we take advantage of our results when we want to develop better algorithm for probabilistic automata, for example, bisimulation, minimization, model checking? And so the answer to this question is that we already have an application, which is not in the LICS paper, but we know that the result holds. So up-to techniques can be used, even if the distributive law is a weak distributive law. This means that soundness of convex up to hull technique holds. So this was already known since 2017 paper, but our frameworks yield that any construction obtained from weak distributive law will yield a sound up to technique. And so this allows to check quickly that if there is a bisimulation between systems, like in the article of Bonke and Puss, where they do this for non-deterministic automata.
Okay, thank you. Are there other questions?
Yes, so the the convex power set is itself a convex set, but it's not a real convex set because it's not cancelative, so you cannot embed it as in a vector space. But if our original set is compact and you restrict to the closed convex subsets, then you can actually show that this is a real convex set. And then you can ask the question, is it compact itself? Would it be helpful? I need to know the extreme points of the extreme convex subset, so to say.
So I do not know many things about this. Are you suggesting to try to work in a different category, for example, compact spaces?
No. Well, just think about the power. Just think about the convex power set, right? And
yeah, okay.
just change it that you don't take all subsets, but just the closed convex subsets. And then, of course, you have to start with something that makes sense. So you have to start with just convex sets which are real convex, are like part of a locally convex space or something. But have you thought about it or
no, not at all. I'm sorry. So I do not know what to answer to this question actually. But thanks for your question.
Okay, thank you. Are there other questions? Okay, so I have some questions. At the end of your talk, you said something about ongoing works. So you've already said that the up to techniques is solved, but well, you mentioned compositionality, and I didn't know what you were referring to. I mean, compositionality is okay, but what kind of results you want to prove, or what kind of issue you want to tackle?
Yeah, okay, thanks for this question. So what I meant by compositionality is that there is a way to compose distributive laws. I refer to a paper of Eugenia Cheng, who proved that provided some diagram called Young-Baxter diagram commutes, you can take one distributive law between two monads, one other between two other monads, and provided the monad in the middle are the same, you can compose it in some way and obtain a distributive law between the two extremal monads. And so this works well in the case of distributive law. And what we proved recently, but it's not published for the moment, is that you can have such a result, but in a very weak form. But the idea is that we can restrict weak distributive laws to be weak distributive laws between a monad and a functor instead of a monad and a monad. And if you do this, you can compose two distributive laws to get another third one. But
okay.
Okay.
What kind of monads you want of distributive laws you want to compose? I mean, do you have an application in mind, or it was just a matter of? I mean, it's an interesting theoretical question, but
yes.
Did you have some concrete distributive laws that you wanted to compose?
Yes, actually. So our example in the LICS paper is for probabilistic automata. But another example which has caused much problems is for alternating automata, using that they would like to use a distributive law between power set and power set, but there is not. So the compositionality results allows to use. Okay, we know that there is a weak distributive law for power set, and power set. And we also know that there are many strong classical distributive laws between power set and machine functor, things used in the modelization of the modeling of automata. And so you have this weak distributive law PP, this other law, and via our abstract result about compositionality, you can compose them and get a new distributive law that is fully explaining alternating automata.
Okay, great. Thank you. Are there other questions? No, I still have a little one. Okay. You can answer briefly and we can discuss about that later. It's about continuous probability distribution. So you mentioned that you want to go into this direction. So I wonder what kind of probabilistic automata you have in mind, or if it's just a matter of you know how to do in the discrete case and you want to go to the continuous case, or if you have some in mind some applications in automata.
It's rather the second option. We just try to go into continuous to see that if the results still hold. But I think there are interesting automata in compact Hausdorff spaces, for example.
Okay, and actually there are also questions in probabilistic programming language which are related to non-determinism and probability. So that might be a good idea to go in
okay, thank you.
Direction also. So if there are no other questions, then we can move to the next paper. Thank you very much, Alexandre and Daniela. That was a very nice
thank you.
talk and paper. Okay, so let's move to the paper on approximating value of generalized reachability stock. And okay, and Maximilian is there, and you can present your paper briefly.
Can you hear me, and do you see my screen?
We see your screen and we can hear you.
Perfect. So our work is on, as you see, approximating values of generalized reachability stochastic games. So what does it mean? It means that we have a stochastic game which contains of states of two different players called minimizer and maximizer. And there's also stochasticity involved. So we have some probabilities. And the goal that we have is that maximizer wants to maximize the chance to reach all the target sets. So here we see there is a target set T2, and these two states are in there, and there is a target set T1, and these two states are in here. So maximizer would prefer to reach the state that is in all of it, but he actually might not be able to achieve that, as it's partially contradicting. And what you do then is that you have a Pareto frontier, which is like you have this curve that models all the Pareto optimal outcomes. So for example, if we care only about T1, we can certainly reach it. If we care only about T2, we reach it with 0.7. And then this curve is like all the optimal trade-offs that we can achieve. So what we want to get is we want to get this Pareto frontier, as it gives us the best kind of information we can get. And the existing algorithm approximates it from below using value iteration. But the problem is that there is no, or there was no stopping criterion. So we could never know whether we are close to the Pareto frontier or not. And our contribution now is a convergent over approximation. So that means we start by assuming that we can reach everything almost surely. And then we reduce this until we reach this point where you are epsilon precise in all directions. And then you know that you're really close to the Pareto frontier, and you know that you can approximate the values of generalized reachability stochastic games for arbitrary small precision epsilon. And just to say that, the hard part is that there can be multiple fixed points from above. So that was the most involved part, was to figure out how we can actually make the over approximation converge. So far, so much for that.
Okay, thank you very much. Are there questions?
So I saw that there was one question on Slacks.
Yeah, there is one question on Slack, so we can start with that. So it's a question of Chen Fu. It's a question about the rate of convergence. I can read it for you if you want. So for a generalized reachability stochastic game, you compute an epsilon approximation of its Pareto frontier. In the algorithm, you report both under and over approximations on the frontier. Do you have any conjecture about the rate of the convergence?
Yeah, so we do have some kind of conjecture. So there are certain things that we definitely know. So for example, in the single dimensional case, we know that value iteration is x time complete. So it certainly takes exponential time, exponential in the number of states to make this converge. And in the single dimensional case, we can also show that it's in exp time by saying, well, there is some smallest possible transition probability and some longest possible path. And then we just take this path and say, well, we have to make at least this much progress. And this is how you know how fast you converge. And the problem in the multidimensional case is that you might need infinite memory, and you might play an action with a very, very small probability. And so we actually don't, like, this is the crucial problem, to get our hands on this very small probability that we play the action with, and we assume that there is a way to classify this, and it will probably also be exponential in the number of states, and probably then somehow maybe even doubly exponential in the number of states or something. But yeah, as soon as we can get our hands on this minimal action probability, we can just lift the proof from the single dimensional case and say, okay, we make at least this much progress. And the way to get rid of the infinite memory is to just say, at some point, we don't care. We have the epsilon to know this is how precise we want to be. And then at some point, the probabilities become so small that we can stop caring.
Okay, but you answer about theoretical rate of convergence. Have you implemented your algorithm and tested it and compared it with other algorithms, or?
Not yet. So currently there is, I think, no implementation of this. I think Prism Games has some things for multi-objective stochastic games, but right now they can't output Pareto frontiers, if I'm correct. At least the last time I looked, I didn't find it. And so there's nothing really to compare to, because like the thing that we build on is currently only a theoretical algorithm. And then the big problem for the implementation of our algorithm is that that this over approximation, like you have to do a lot of geometrical things actually to figure out how you can converge. So this might actually take a lot of time unless you know exactly what you're doing, and like exactly what you're doing in the sense of how to implement these things efficiently. So this is why right now we don't have a prototype, but purely focused on the theory.
Okay, but depending on the stochastic game you are considering, do you have some situation where the geometry could be easy to solve and your implementation efficient enough to test it? Or
so if you don't have probabilistic loops, then it's really simple. Then it I mean, then you
sorry,
can
what do you mean by probabilistic loops?
Probabilistic loop means that with some probability you go back where you came from. Okay. So this might be just with some probability you go back to yourself or to someone who came before you. And if you don't have this, then it's like you just take linear time in the number of states, and then it's really easy. And if you have the probabilistic loops, then I don't know any other class of games where I would say this is really easy. Or this is something that we could definitely do, because as soon as you have those, it just becomes very complicated. I mean, the other thing I can say, if you don't have end components, then you don't need all the geometry that we introduced. This is basically, so for games without Shor cycles, without end components, the method of the previous method of Kwiatkowska and Chen and Fureit and so on, it converges. So then we would just have to implement their method.
Okay, so if I understand well, you don't know how to define heuristic depending on the geometry or the description of your game.
No, we have not thought about that.
Okay. And last question, if yes, I can. So, what are the next steps in your after this result?
Mm-hmm. So definitely want to prove something about the rate of convergence or the complexity of this algorithm. Mm-hmm. And then the main open problem, like the dream goal, is to figure out whether the computing the precise Pareto frontier is decidable or not. But right now we don't have any attack vector in our hands for that. But we have several other things that we can consider that might help us. So one thing is we actually consider here the lower value problem. So this means these games are not determined. So it matters who fixes the strategy first, whether we fix first or whether the opponent fixes first. And we consider the worst case, that we fix first and the opponent can react, which is actually the harder case. And while looking at that, we actually found some results for the easier case as well. So these are things that we plan to write down properly and expand. And other things you could do would be to consider other objectives.
Okay. Thank you very much. Are there other questions?
I have a naive question.
Yep.
That is about, I think that for parity objectives, there exists also some results on this kind of problem. When you have compute the Pareto frontier of multiple parity objectives. And here they use linear programming. Why is it not possible to use it here?
I guess that for the parity, you would probably have some restriction that you only look at almost sure parity or something like that, because otherwise I think it even becomes undecidable. And what I can definitely answer is, why can't we use linear programming? Even in the single dimensional case, linear programming does not suffice because of the interleaving of the players. So it suffices for Markov decision processes, so games with a single player. But even for normal stochastic games with a single objective, you already need to look at quadratic programming because of the interleaving of the players. And yeah, and so you could probably also make an algorithm based on quadratic programming for this problem, but value iteration is the most commonly considered algorithm for solving stochastic games.
Thanks.
Okay, thank you very much. If there is no other question, then we can move to the next paper. So thank you for this paper.
Thanks.
So the next paper is mixing probabilistic and non-probabilistic objectives. And I think Raphael will talk about the paper. You have 2 minutes. And
yes,
you can
I share my
share
screen?
Yes, you can share your screen.
I first have to stop sharing my screen, but I don't see how I do that.
I think somebody else can go and share their screen.
Yes.
No, I cannot. I'm told that I cannot.
So in some previous, they had the same problem in some previous thing. Here it says stop. Okay, now I found it.
Thank you.
Okay. Okay. Can you see it?
Yes, we see it and we hear you.
Perfect. So quickly, we've already seen a bit about what happens for where is it? Yeah. For almost sure objectives. So here I look at Bushy, but we look at parity in general. And in the Markov decision process, the idea is that you want to visit some states infinitely often with probability 1. This is pretty classical. And to do so, you just want to find some loop. Another problem that is also can be looked at is when you want to be sure to have the same thing. The difference here is that you cannot just have probability 1. So for example, if you have a loop, it may not be enough because you may get unlucky and always come back here and so you're not sure of visiting infinitely often this green state. And so you would have to rely on other way to do it. And we are looking at the question of finding strategies for Boolean combinations of sure and almost sure objectives. So to do so, we have used the notion of n components. And the main idea of our proof techniques is to break up the Boolean combination in subformulas, find n components corresponding to these subformulas, and then come back to whether or not we can satisfy it in all the game, in all the MDB. With this, we managed to synthesize strategies for Boolean combination of sure, almost sure, and as we have negation in the Boolean, we also have non-zero and existential objectives. And to do so, we need randomized infinite numeric strategies. The main problem needs it has a complexity of NP with an NP oracle. But we also have 2 interesting subcases that are the case where we have a conjunction of only almost sure and non-zero and existential. So we have no sure case, and here it is in P. And when we have only one sure condition, we have an P intersect NP the complexity, that is, we only have to solve a parity game. And in future works, we may look at probability with a threshold or other conditions.
Okay, thank you. So are there questions? So if there's no question now in Zoom, we have a question on Slack.
Yeah, which I put in the.
Yes. So I can read it for you if you want. So first, your work is nice. A question from Chen Fu. So you consider the problem of finding strategies to satisfy a combination of objectives on an MDP. Could you give some practical examples for this problem? And second question, why do we need the combination of probabilistic and probabilistic objectives? So first, practical examples, and then why probabilistic and non-probabilistic objectives?
First answer to the second question, because I think it implies the first one somehow, because why do we want sure and almost sure mainly? It is because almost sure objectives, or probabilistic objectives, are what are like in the real life is what you usually want for most cases. You want to have something that works correctly in most cases, but you also sometimes you want to have some constraints, some hard constraint that will be enforced whatever happens. These are the sure objectives. And so when you have some system that must satisfy a normal behavior and have also some constraints, you may want it to satisfy a Boolean combination of these objectives. So that's why we look at these problems. Now, is there a direct application? I'm not sure that we can say that what we are doing here has any direct applications. That's why we have to look at some extensions. Because in practice, the priority one is a bit too powerful. Usually we may want to have some threshold, we want to have something a bit less powerful than one. Objectives that are just parity, maybe a bit too complex or a bit too simple in some cases. And then there are also some problems about, for example, that we are looking at the full Boolean combination. The conjunctive cases, subcases, are probably more useful in practice. But still, Boolean combinations are meaningful. So for example, we may have to either satisfy a main job or satisfy some kind of a fail-safe job and raise some alert. So this is just, and both with some probability or some sure cases. So that's why it makes some sense.
Okay, thank you. So are there other questions? Okay, so I have a question. So you, I mean that there were already some tools for solving the non-probabilistic objectives. And what kind of new techniques you had to introduce for adding the probabilistic objectives and the mixed ones?
So the idea is to have all of this be more or less independent in some way. We will first find probabilistic strategies, then we'll find some suitable end components, where we'll create a new strategy that must be enforced surely somehow, or more than one, and then here we'll solve it. So first we call a black box that is the probabilistic solver, and then a second black box that is the sure solver. And as we act on this as black boxes, this is we don't bring them anything, but anything they can bring, we gain it.
Okay, so that there is not really mixing black box that compose well.
Yes, we are finding a way to compose the black box without having to open them.
Okay, thank you. Are there also questions? So okay, thank you very much, Raphael, and I think we can move to the other paper. And the next paper is by Gianluca and Michele. It's the benefit of being non-lazy in probabilistic lambda calculus. So I think, Raphael, you have to unshare your.
I don't find
your
where I can do.
Yeah,
okay,
thank you. So Gianluca, if you want, you can share some slides. Yeah. Okay, thank you. And you have 2 minutes to present your paper.
Okay. So my talk is about the full abstraction result relating contextual equivalence and probabilistic applicative bisimilarity in the non-lazy call by name probabilistic lambda calculus. That is the probabilistic lambda calculus endowed with the standard head reduction strategy, where probabilistic applicative bisimilarity is just probabilistic bisimilarity in a very special label Markov chain, which is the one associated with the probabilistic lambda calculus. And so in a sense, this full abstraction result witnesses the discriminating power of non-laziness, because in the lazy call by name probabilistic lambda calculus, full abstraction fails. In particular, soundness is established by means of a context lemma, so without relying on Howey's method, which is a standard technique. And we also need, as you can see, an applicative property about bisimilarity, which is based on a lemma about probabilistic assignments by the Lagon authors, that allows us to correctly decompose and recombine subprobability distributions of observables. Concerning completeness, we do not use the standard notion of testing equivalence, but we rather adopt the Levent's separation theorem for probabilistic Nakajima trees. And this allows us to move from the contextual equivalence to the probabilistic Nakajima tree equality, where intuitively a probabilistic Nakajima tree is a kind of infinitely expanded Bond tree. We also showed the failure of the inequality full abstraction, because as you can see, probabilistic applicative similarity is sound but not complete with respect to contextual preorder. And this result can be established by means of a counterexample, which is a kind of tailor-made version of the one for the failure of full abstraction in the call by value setting. And we also conjecture that by extending the probabilistic lambda calculus with a variant of Plotkin's parallel OR, one is able to recover this asymmetric version of full abstraction, as already proven for the call by value setting. So I'm done. Questions?
Okay, thank you very much, Gianluca. Other questions? So you have a question on Slack by Professor Fu. And you've already replied to that. So perhaps you can make a short summary of the question and your answer.
Yeah. So the idea is that in principle, one can establish probabilistic applicative bisimilarity. So we can check that if two programs are probabilistic applicative bisimilar quite easily, because we just need to find probabilistic applicative bisimulation that relates to programs. While concerning the contextual equivalence equality, we need to check any programming context. And so we have infinitely many programming contexts, and so it is not so easy to check contextual equivalence. But we couldn't find how to show a concrete example in the paper showing how easy it is to establish this equivalence, which is the probabilistic applicative bisimilarity relation. We have an example, which is example 7 in the paper, about in which we proved that the identity and its expansion are probabilistic applicative bisimilar, and indeed we showed a probabilistic applicative bisimulation that relates them. But if you look at the proof of this in this example, then this proof is not shorter with respect to the one establishing contextual equivalence for these two terms. So actually the problem is that while in the lazy call by name probabilistic lambda calculus, we have plenty of examples showing how probabilistic applicative bisimilarity is easier with respect to contextual equivalence to establish. Here in the non-easy setting, we couldn't find a good example showing this, that fits this picture.
Okay, thank you. Are there other questions?
Yes, I have a question actually.
Okay.
Okay, so you show that you have full abstraction with respect to contextual equivalence, but not with respect to the asymmetric version. And interestingly, the situation is the same for probabilistic PCF and probabilistic coherent spaces. Do you think the two phenomena are related? Because before in denotational semantics, I know of quite few situations where you have full abstraction with respect to the equivalence, but not with respect to the observational preorder.
Yes, it might be the case. I don't actually. I'm not. I don't have a good example showing this. How the two inequality, the two results showing the failure of this inequality full abstraction are related. But yes, I think that they can be related. Maybe one can exploit the. Yes, let me think a little bit about this question, because I think it is so interesting. Yes, I currently not able to figure a connection between the two phenomena, but I do think that they are closely related.
Okay, thank you.
Yeah, I have also a question about you test the equality of probabilities, and what it's the same question as for Charlie's. What about the distance between probabilities? I mean, is it the right question, contextual equivalence, to test if two probabilities are two probability distribution are exactly the same, or you can think of other contextual equivalence and related Bisimulation that you could relate?
So I'm not completely sure to understand. So
if you want to test if two probability distribution are equal, you have to compare for each sample if it's exactly the same probability.
Yeah.
Okay, but it's hard to test if two probabilities are exactly the same. They can be close, but it's hard to know if they are exactly the same. So one question is sometimes if you can compare the distance between two probability distribution, and are there some work in the Bisimulation world and for the contextual equivalence side? And does your result can your result be extended to that kind of situation?
Well, actually, I don't know, but I think it's can be interesting to find a connection with this framework. I mean, I think that one can. I don't know. I think it's interesting to find to work in this framework, but I actually don't. I'm not able to find a good answer to this question, because.
Okay, no problem. And so, Michele, you want to say something?
I had a remark about this point. I think. So as Gianluca said, we don't know whether we can extend this kind of results to distances, metrics, but there is an essential ingredient in our work, which is Levin-Pease separation theorem. So if we want to try to generalize our approach to distances, one has to try to understand what does it mean, how to extend the separation theorem to distances. So whether it is possible to define a kind of metric space over Bohm trees or Nakajima trees.
Interesting.
It can be nice, but yeah. I don't know whether in the literature this approach has been studied.
Okay, thank you. Are there other questions? Okay, so I think we can move to the next paper. Thank you, Gianluca. And so last paper is by Bas, I think. Yes. Bas, okay, you can share your slide and you have 2 minutes to present your paper, a characterization of ordered abstract probabilities.
Yes, thank you. So what is this about? Oh, let's see. Yes, why, if you have probabilities, are they always from the real unit interval? That's the question. And we think we might have a answer. So we have a set of axioms, reasonable axioms, which are reasonable if you have probabilities, that if any set of probabilities satisfies them, then either they have to be the 2-element set or the real unit interval. So why did we get to this? We got to this because we were thinking about a axiomatization of quantum theory from a computer scientist's perspective. And then these axioms follow naturally. Then we get naturally these axioms on the scale, on the probabilities. So it's not that we just chose axioms to make it work. It was, so to say, forced upon us. Well, we explain a bit more about this in our talk. And one of the crucial axioms is that we assume our probabilities to be sequentially complete. So if you have an ascending sequence of probabilities, then there should be a supremum. So we could have called it a characterization of sequentially complete or abstract probabilities. Anyway, then we go through the, we mentioned some applications. We go through the axioms. Basically, there's a plus and a multiplication, which satisfies some reasonable things. We don't assume commutativity. We do assume a certain kind of distributivity while we go through them. And our important one, of course, is the sequential completeness. And these are not yet all the axioms. So if you leave out the last 2 axioms, then you already get a quite interesting thing, which is called an omega complete effect monoid. So that summarizes all but the last 2 axioms. Examples of these are omega complete Boolean algebras and algebras of continuous functions to the unit interval. And actually, these are all examples. So if you have something that satisfies the first bunch of axioms except of the last 2, then it must be the direct product of algebra of continuous functions and an omega complete Boolean algebra. And that's basically the meat of the work. And that's the main result of the paper, so to say. And then the rest is just, the last axiom is just to pick out a single point, and then you get either the real unit interval or the 2-element set. So yeah. Okay, then we continue to go through some highlights of the proof. The main theorem that we use from the literature is Yoshida's representation theorem of lattice-ordered vector spaces. Another interesting thing is we have a little formula from the infimum, which is also valid in the real unit interval. So this is pretty funny. The perp means 1 minus. So this gives you the infimum of two numbers, which is, I think, quite cute. Then we discuss the proof, how it works. Another interesting thing which I discuss in the talk is a partial division, which is quite interesting. And that's about it. So watch the talk if you haven't any questions.
Thank you for this short presentation. So are there questions? So I think Noreen is here.
Yes, exactly.
And you had a you had a quick not quick you had a description of Slack. So perhaps you can tell us about what was it about, and you can discuss with us.
Ah yes.
Sorry. Should I post the question again?
Yes, yes. If you can sum up your question, it would be nice.
Yeah, basically, because of this motivation of quantum theory, I was wondering how that fits to this sequential completeness assumption. But I already got an answer on Slack, so everybody can read it up. But I guess it would be nice if you could go over it again. Thank you.
Yes, please.
So basically, quantum theory is formulated using the real numbers as assumptions, as being the probabilities. Also, in all existing reconstructions of quantum theory, they just presuppose that the real numbers are the set of probabilities. But that would be an easy answer. The thing is it really required? And I would think that that quantum theory does not really support or reject that the probabilities have to be sequentially complete. So I think it's independent. Or well, at least there's no evidence either way. It's just convenient to have them, right? Because then you can have a sum, which is nice to sum a series, right?
Okay, thank you. Are there other questions? Oh, Noreen, you want to say something?
No, thanks for the answer and also for your explanation in Slack. Thank you very much.
Okay, so are there other questions?
Maybe a naive question. So if you go to various talks, or maybe you Google, you spend some time Googling or something, and you come across negative probabilities and complex probabilities and that sort of thing. So clearly, some people are using these these probabilities, and they're presumably making some sense out of them. So how does this? I guess this does not necessarily contradict, of course, what you've proven. I guess the question is, how does one reconcile the existence of these alternative views of probabilities with what you've established in your paper?
Well, yes, then one of the axioms must fail, of course. And well, for instance, one question is that some people understand in quantum theory they use complex numbers as amplitudes, right? And people think they are like generalized probabilities. That's one way they think about it. But actually, I would think that they're not. Well, it's a way to think about it, to make it easy to have in your mind, but they don't really behave like probabilities, like real probabilities. And also with negative probabilities, there's not really something breaks, which is quite obvious. Yeah, I can't from the top of my head give the way it breaks now in a few minutes, but we can just go through the axioms. Yes. So I think one of them is that if you have an event, for instance, then an event should have a certain probability, right? And then you have the event that it doesn't happen, and you want that it has a probability which is the opposite, 1- of it, and you would like that this one is unique, right? So this is one of the axioms which would fill. Let me see, for which one would it fill? Would it already fill for the negative ones? I guess. Yeah, I'm not. Also, that there's an implicit order already, because with the axioms you already get an implicit order, which also is nonsensical with the complex one. So sorry, I can't answer this very sharply.
Okay, thank you. So are there other questions? So I have a question. So you start your talk by saying that you want to describe quantum types and categorical axiomatization. So I was wondering what kind of quantum types you were starting from. So my question is, how did you decide what are the right axioms? So what was the way you come to these axioms, and how you know that it is the right axiomatization and you have all the axioms you want, or not too many? Is it complete? Is it can you get rid of some axioms and so on?
Yeah, so none of the axioms are redundant, which we listed now. But it's a good question how we got to it. So there's for the finite dimensional case, so if you have finite dimensional quantum theory, then there's general agreement, which should be the category of quantum types and programs. Finite dimensional C-star algebras with completely positive maps between them, or any small trivial variations on that, which don't really change the thing. And also most reconstructions reconstruct this like finite dimensional quantum theory. But there's basically no reconstruction which does it for infinite dimensional quantum theory, so where you can have more than, it would be nice to, just like we like to work with natural numbers, right? Where it's not bounded. It would also be nice to have unbounded quantum types. But then there's not general agreement what should be the proper category. There are suggestions like phenomenal algebras and a few others. But the interesting thing is that none of the properties that usual reconstructions use translate to infinite dimensional. So these axioms which are used finite dimensionally of the existing reconstructions just don't hold infinite dimensionally. So actually, very few things hold. There's very little structure in this category. And so we just look at any structure that we can pull out anyway, and then this naturally leads to some assumptions on the scalars. At least these are really the axioms here, which cause this are quite simple. So there's not. The only non-obvious one is the sequential completeness, I guess.
So I see. I see now how you came to these axioms, but how do you know that? Don't know. I'm looking for a kind of correction theorem that says that if I have a quantum system, then this axiomatization is representing it, or something like that.
Well, well, if you just think about the probabilities, then it's most people would just say, oh, probabilities with quantum theory are just the real unit interval. There's no doubt about it. So in a sense, that's a bit of a, but that is like a simple way out. So the axiom where it comes from is we have a category which is an effectus, which is a bunch of axioms, and that are really weak axioms. So basically anything that looks, any category that has a co-product which looks a little bit like probabilistic combination satisfies this already. And then if it also, the maps are sequentially complete, which you would like to have if you do domain theory, right? Because you want to be able to give semantics to a loop, right? By taking the supremum of doing several steps. So then if you have a omega complete effectus, then the scalars in there, the set of probabilities in there that maps from 1 to 1, they must be satisfy our axioms, well, the brunt of it. So it's not really something about quantum theory necessarily. It's just quite weak, I guess.
Okay. So thank you very much for your answer. Are there other questions? Okay, so I think it's the end of our hour. So I want to first to thank Bas for his explanations and answers, and I want also to thank every speakers to come and people that attend to this session. It was very nice, and I think Michael has sent a link to go to the social meeting, and so bye and enjoy the LICS and ICALP meeting.
Yes, thanks. Enjoy the evening and the social meeting. You find the link in the chat. Thank you all. Bye.
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 Thanks a lot for your moderation.